Anyone want to talk on protein charge? Free of charge. So today I want to talk about the isoelectric point, or the PI, as well as the pKa, and what a basic and acidic amino acids are, and basic acidic proteins, and all this terminology that we use, and how we can figure out whether a protein is overall net positive or negative at a certain pH, as well as what's happening at the individual amino acid letters level.
Proteins are these long chains of amino acids or protein letters, and they have these different properties, and they're going to influence how the protein folds and functions, because different proteins have different numbers and combinations of these letters. And one place this comes into play is when trying to think about a protein's charge. So there are 20 common genetically encoded amino acids, and only 5 of them are sometimes, we think of as being sometimes charged. Although like cysteine can like get activated and stuff, as we saw with the cysteine proteases, and same with serine and threonine. But like at physiological pH or bodily pH, those are normally just like totally neutral. It's just like in those enzyme active sites and stuff that you can see that happen. But the ones that we need to worry about for charge are going to be aspartate and glutamate. Sometimes we'll see aspartic acid and glutamic acid also see, and these are referred to as what we call acidic. And then the basic ones are lysine, arginine, and histidine. And so what do I mean by acidic and basic? Well, this actually relates to how these get their charge. And so the terminology can be kind of confusing. So as I talked about before, so pH is a measure of proton availability. And so protons are H+, and pH, it's a inverse log 10. So the more protons you have, the lower the pH. And in fact, for every pH decrease of 1, you have 10-fold more protons. For every pH like raise of pH, you have 10-fold less protons. So because it's this log 10, you might think like, oh, a little pH difference won't matter that much, but in terms of the actual molecules going on, yeah, so for each pH change of 1, that refers to a 10-fold change in the amount of protons. And so why does all this matter? Well, these amino acids, so you can see here that I've drawn them in their charged form and their neutral form. So they have this charge in this neutral form that varies only by a proton. So in their acidic form, they're protonated, they have the proton. And then if they give up that proton, which we call acting as an acid, so if they act as an acid and give up that proton, now they become their conjugate base, which is, in this case, the case of aspartic acid and glutamic acid, that is negatively charged. So we call them acids because we're referring to their neutral form. In their neutral form, they're acidic. They act as acids and give up a proton. But when we see them in our bodies and that sort of thing, we almost always see them in their conjugate base form. We call them acidic though, because that's based on their name. So that can be really confusing if you're like, what is the heck is acidic? So we call aspartic acid and aspartate and glutamic acid and glutamate, we call these acidic. So the reason why at a bodily pH they are negatively charged is because they have a really low pKa. And so now we have to introduce another concept, this pKa. So basically the pKa is the pH at which half of a molecule will be charged, or which a molecule has like a 50-50 chance of being charged. So a pKa is a measure of the acid strength. So there are different acids can have different strengths, which tells you about how much they want to keep the proton versus like give up the proton. So if we go back to our proton jar, so think about something that would be acidic. So an acid is something that is going to donate a proton. But what if the proton jar is already really full? This is the case with a low pH. In this case, even though it wants to donate a proton, there's kind of already a ton of protons, and so it might just like hold on to that proton. Or if it does give up a proton, there's one right there, and so it picks it right back up. So the more protons that are available, the more likely it is to be protonated. This is true for everything, but different acids have different like willingness thresholds, kind of, you can think about it like and the pKa is where they're kind of like on the fence. If you go above the pKa, then you're decreasing the amounts of protons, remember, because it's an inverse log scale. So if you go above the pKa, you're decreasing the amount of protons. And remember, the protons are where the positive part comes from. And so if you have more protons, now you're going to have more protons available to protonate this and put it back into its neutral form. And so, but these pKa is the value at which you're half. So above the pKa, there are fewer protons available, so it's less likely to be protonated, and you're more likely to see it be negative. Below the pKa, you have more protons available, and so it's more likely to be protonated. So, and remember, the protonated form is the neutral form. If we look at the pKa of aspartic acid and glutamic acid, we can see that they're around 4. Bodily pH is around 7.4. So if we have an increase of pH, we can actually use this thing called like the Henderson-Hasselbalch equation. I'll show you more later maybe. But so a pH, if it's like 3 above the pH, that's 10 times 10 times 10. So you have 1,000-fold, you're going to have 1,000-fold more of the deprotonated form than the protonated form. So you're only going to have like 99.9% in the deprotonated form, if I did that math right in my head. So basically, it's almost always going to be deprotonated. Okay. So what if we look at the basic one? So these are going to be positively charged. So we can see that they have these pKa's, these really high pKa's. So this means that, so remember, in order for it to deprotonate or to predominate in the deprotonated form, what that means is that we need to be above the pKa. These have a pKa of like 10.5 and 12.5. It's ridiculous. So our body, we're not going to have like overall a pH of greater than this. And so these are almost always going to be in the positive form. Histidine is an interesting one because its pH is closer to physiological pH. Its pKa is closer to physiological pH, so it can actually exist in both forms. And all of these can play roles in, so although we're talking here about like the overall pH, but when you have a protein all folded up, you can get kind of like local pH, because remember, like the pH is a measure of proton availability. And so if you're thinking about that as like a big proton jar, yeah, the pH, and looking at the overall pH, you might think the pH is one thing. But say you were to just take a like little sample of the jar or whatever. What if your sample, you happen to take a sample where like more of the protons were hanging out in that part? Then you would have you could have local differences in the pH. And I'm not talking about just like in a solution, but when you have a protein all folded up and stuff, the amino acids next to it are going to contribute. And so say if you had an amino acid next to it that can contribute a proton or that sort of thing. So you get this local pH effects in a protein. And this can help, this with the like cofactors and other things can help to change the local pH and affect whether it'll be protonated or deprotonated. And so this is really important for activity stuff, like making things do things, because if you can like give and take a proton, that can be really helpful for making reactions happen, because it can make things like more reactive or less reactive or whatever. So this is talking about at the amino acid level. So we're talking about the pKa at the amino acid level. So when we talk about pH, we're talking about at the solution level, or we can talk about like local pH, but typically when we're talking about the pH, we're talking about like at the overall solution level. So like my buffer says my pH, or my pH meter says that it's 7.4 or whatever, you know? So, and then when we're talking about pKa, now we're talking at the individual amino acid level. And we're talking about, is this likely to be protonated or deprotonated? And so we can, and then we can figure this out using like the Henderson-Hasselbalch equation. And so this is where those numbers that I was talking about come in.
Move this part to the end so that I didn't bore people unnecessarily.
So we talked about like the solution level, so the pH. We've talked about the amino acid level, so the pKa. And now if we're thinking about a whole protein, we have this term called the pi. So the pi is basically the protein analog of the pKa. So it's the pH at which a protein is neutral overall. So remember, when you have a protein, it's all like folded up into this unique shape. So you can have, and different proteins are going to have different numbers and combinations of positive and negative amino acids. And these are going to be like various places on the protein. So you have some combination of positive and negative. Because these have like different pKa's, they all have different pKa's. So at a various like pH, some of these could be negative, some of these could be positive. And so these all are going to differ at different points. And if you go up, like if you change the pH and titrate it or whatever, they'll change at different places. And so you can have some going positive and some going negative, and it's all this stuff. But at some point you'll have a pH at which the protein is overall neutral. So the amounts of positive balance the amounts of negative. And we call this the isoelectric point, or the pi. So this doesn't mean that protein doesn't have positively charged arginines and positively charged lysines. It does. It doesn't mean that it doesn't have negatively charged aspartate, negatively charged glutamate. It does. Instead, what it means is that overall the protein is neutral, so the charges cancel out. But you can still have like charged patches and stuff. But the pi, the isoelectric point, is the point at which a protein is neutral overall. So different proteins are going to have different pi's because they have different amounts of these positive and negatively charged. So if you have a protein with a higher pi, we tend to call these proteins like basic, similarly to how we call these basic. And so these proteins are more positively charged. So let's think about why. So remember, the pi is the point at which it's neutral. If you go at a pH above the pi, now you're going down in the proton availability. And so the protein starts picking up more negative charge. If you go below the pi, then your protein there are more protons available. And so so the negative things will start taking them and getting neutral. The neutral things will start taking them and getting positive. So overall, your protein's getting more positively charged. So if you have a protein that is above it has a high pi, this means that like when you're working with it, so if your protein has a pi of like 9 and you're working at a solution of 7, your protein overall, more of it is protonated. And conversely, if you have like an acidic protein, it's going to be like typically negatively charged overall, because if you have a low pi, this means that in order to get it to be positively charged, you need to get it below, well, on average, you need to get it below the pi. And if you have a low pi, getting below that is going to be like not great for the rest of the protein or the cell or whatever. Because you need that low pH in order to get it to protonate, because it has this low pi. And at a low pH, remember, it's that inverse log 10. So the low pH means there's more protons available. So if you have a quote unquote acidic protein, it's more likely to be negative. If you have a quote unquote basic protein, it's more likely to be positive. And we typically refer to these just like it's all relative, and it all depends, remember, on what pH you're working at. But typically we use these when it's like in comparison to like physiological pH or whatever, which is around like 7. And But remember, this is the overall pH, the overall like PI and the overall charge and all this stuff. And we're not talking about at the individual level. And so this is important because you can have like patches, like basic patches and acidic patches, and these can have like big physiological relevance. So they can be like really biologically important. So I want to show you an example. So there's this tool called Param, and I've talked about it more in other posts. But basically, it allows you to calculate like a bunch of factors for a various protein or even for like a sequence. So if you make changes to a protein, like site-directed mutagenesis, you can figure out it just from the sequence, and so figure out what changes, how your changes affected things like the isoelectric point. Or if there's a protein that's already like a normal protein or whatever, you can just search for it. And so I search for human AGO2. So it's going to calculate the parameters and this sort of thing. And one of the things that it'll tell you is the theoretical PI. And so the theoretical PI is 9.32. If we go back to our talk about this, if we have a pH, so our pH is above 9. So that's going to put us in the basic camp. So it's going to be a basic protein, and it'll have an overall net positive charge. And so you can actually see kind of why this is. Okay, so this is Chimera X. So I've talked mostly about Pymol, but Chimera X is another like tool that you can use to visualize proteins, and it's really good for displaying like if you put like electrostatic. And so the way that coloring is done is if you have positive charge, that's going to be blue, and if you have negative charge, that's going to be red. So if you look at argonaut, you can see that it's got a lot of blue, which means that you've got a lot of positive charge. Especially in this middle region. So you can see there's kind of like this channel going through, and this is where the RNA binds. And so if we show the potential of the RNA, you can see that it's very negatively charged. And so this allows you to have these sort of like this RNA binding pocket. They're perfectly matched for each other. You've got this positive, you've got this negative, and it's a match made in electrostatic heaven. But you can also see that so the protein is basic overall, and it's got this high concentration of basic, but there are also parts that are more acidic, so parts that are more negatively charged. And so proteins, their overall net charge is reflected in the PI, but that doesn't mean that they can't have local patches that are positive or negatively charged. And this can have really important implications for like binding and that sort of thing. One reason why we often look at the PI is when we're trying to determine like what type of chromatography to use, like ion exchange chromatography. So we can take advantage of a protein's charge in order to separate it in this form of protein chromatography. So you have this like columns filled with these little beads, and they'll either be positively charged beads or negatively charged beads, depending on your protein and the pH that you're working with. You choose whether you want the cation exchange, so in that case you have negatively charged resin that binds to positively charged proteins, or the anion exchange where you have positively charged resin that's going to bind to negative proteins. And so you want to use this above the protein's PI and this below the protein's PI, because you want to make sure that your protein is going to be positively charged for the cation exchange, and you want to make sure your protein is going to be negatively charged for the anion exchange. And so you can look at the PI to get an example, to get an idea of where it will bind and what type of resin to use at what pH, because you don't want to go to like an extreme pH because that's going to make your protein unhappy. And so, because often we're trying to work like around the physiological pH, which is like what these proteins are normally used to working with, unless we're talking about like some acidophile or whatever, which those guys are so cool. But anyway, so yeah, but the truth is that when you're doing ion exchange chromatography, you're actually like, it's actually those like local patches that can have a really big effect on what it'll bind. So you can actually have proteins that will bind to both columns So both positive and negatively charged because they have these different patches. And so the PI isn't going to be like your ultimate be all end all. It's not going to like guarantee that your protein will bind to one of the columns or another, or that your protein will bind at a certain pH. But because the PI is overall, but it's definitely a good starting point. And so because my protein is basic, because it's normally positively charged, I use a cation exchange resin. And so this has a negatively charged beads and my protein's positively charged, so it sticks, and then I can compete it off with salt. But that's one place that if we want to, there's also cases where we can, like, the PI is important for like this time the actual like overall charge is important. And one place this is important is like isoelectric focusing. So basically trying to separate a protein based on its PI. And so this is often used with like two-dimensional electrophoresis, where you separate it based on its charge and then based on its size. And so SDS Page, so this is a form of gel electrophoresis I've talked about a lot. Basically with that, you're actually, because proteins use electricity to send proteins traveling through a gel mesh, and it's going to separate them by size because the longer ones are going to get tangled up more and travel slower. And so when you turn off the power and remove that charge gradient, the proteins are stuck in place and the bigger ones won't have traveled as far. But this relies on them being enticed by a positive charge. And since like my protein's already positively charged, so if I were to try to run it without doing anything, my protein wouldn't go in. And I know this firsthand. But if because there's things you can do like native page, where you try to just like separate them as is. But anyway, there are also other methods. I'm hoping to try like blue native page, which you actually have like a dye that binds to them and makes them negatively charged so they can travel. So I want to try that. But anyway, so your proteins are going to be, so proteins have different charges. Some of them are already negatively charged, some of them aren't. But anyway, if we're trying to separate them by their sizes, we don't want them to have different charges that are then affecting the travel. And so we coat them with this anionic detergent. So anionic meaning negatively charged. And so the purpose of the SDS is multifold. So it is a detergent. It's like a soapy thing, and it's going to coat the protein and make it unfold and denature and keep it all happy in its denatured form so it could slither through the gel. And because it has this negative charge, it's going to give it the power to travel through. So we're like erasing its charge. But if we don't erase its charge, there are ways with like isoelectric focusing that you have like a pH gradient gel. And so the protein will move through it until a point where it is at its PI, because when it's at its PI, it's neutral. And so it's not attracted to, it's not like compelled to move. So you have this charge gradient and it'll be traveling through, but then when it's at its PI, it's neutral. And so it's not going to have that urge to travel to the other side anymore because it's neutral and there's no like opposite charge attracting it. So that's one way that PI can come into play. In that case, we're talking about like the overall PI, the overall charge of the protein being really important. Another place where charged residues or amino acids might come into play is, and that you should be aware of, is with the Bradford assay. So basically, and also with like staining gels and stuff. So Bradford, so Kamasi Brilliant Blue is this stain that we often use, and we can use it for Bradford assays to try to determine how much of a protein is present. But so basically it's biased by basic letters. So it has, so basically you have this, it has these two forms. So it's blue, and that we take advantage of this part when we're doing like a Bradford assay to see if how much of a protein is present. But when it binds to a protein, it stabilizes it in its charge, or it's anionically charged, so negatively charged. And then it's negative. Those negative groups are going to like to bind to positive parts of proteins. And so it'll be biased by if your protein has a lot of like arginine, lysine, and histidine. And it can also bind, it'll also be biased by these ringy ones, which will bind to its ringy ones. So that's something to be aware of. So just a little overview. So our acidic amino acids, we have glutamate and aspartate. And so the reason why we say like glutamic acid or like glutamate or aspartic acid or aspartate is because it refers to the conjugate acid form, so the carboxylic acid form, and the carboxylate, or this deprotonated anionic form. And see, they both have low pKa's, well below the physiological pH, and so these tend to be negatively charged. And they can play really important roles in enzymes. And then if we look at our basic amino acids, we have histidine, lysine, and arginine, with histidine being the most wishy-washy on its charge state. So it has a pKa of 6. These guys are really high, so they tend to be positively charged. Lysine, you can get it like deprotonated, and this is really important for doing things like forming shift bases that we talked about. Arginine is like super hard to get it to deprotonate because it's really happy, because although we draw it with like these, we can draw it with like one double bond and one single bond, and the positive charge here is actually resonance stabilized. So these 3 nitrogens are all helping share that charge. And so this is really stable and really happy. This like 1 medium ion. So this is why it's like always positively charged. And then, but remember, this is at the individual amino acid level. Then we have to talk about the PI, which is at the protein level. And that's going to take into account all of the different amino acids that a protein has. And this is why different proteins have different isoelectric points, and thus different charges at certain pHs, or at any pH. I mean, like different pH. Basically, the Henderson-Hasselbalch equation, you typically use it for talking about like buffers and stuff, but you can figure out what proportion of a acid is going to be like deprotonated. So remember, we have like an acid conjugate base. So when acid gives up a proton, it becomes its conjugate base. A conjugate base takes the proton, it becomes its conjugate acid. And so we can represent like a generic acid as HA. And then that would, if it gives up a proton, now it's A minus. And so we can have this equation where we have the log 10 of the A, the deprotonated over the protonated. And so this allows us to connect the pKa and the pH in order to determine like what proportion will be protonated at a various level. And so if you rearrange things and then take the anti-log of 10, this will allow you to see like what proportion will be protonated or deprotonated. And so the whole thing with pKa, this is how you can see that if you were to do this with the pKa, at the pKa, you wouldn't have any difference. And then, so your anti-log of 10 would be 1. But if you were to go like 1, you have 10-fold. So you see like for every increase, for every pH change of 1, you have you have that like 10-fold change in the pH. And so that's how we get that. So a lot more on that in like my buffer post. So you can see why, like, if you take a buffer and then you can have like a buffering range, and then you go out of the buffering range or whatever. So check out that post if you want more. But basically a pH change of 1 leads to a 10-fold change in the ratio of deprotonated to protonated. So if you have a positive change, you're going to get more deprotonated. If you have a negative change, you're going to get less deprotonated. And so a positive change meaning, so you're increasing the pH, and then if you increase the pH, you have fewer protons available, and so your acid is less likely to be protonated. If you decrease the pH, you're going to have more protons available, and so your acid is more likely to be protonated.